All right, hello everybody. Welcome to EEE 135. This week we're going to talk about Chapter 10, Geothermal Energy Sources. So let's go ahead and get started. First thing we need to talk about is what's the definition of geothermal energy? So geothermal energy comes from the Earth's core. The Earth's core is a giant heating device. It's pretty much like a giant fusion stuff going on at the center, and the heat radiates out towards the surface, right? There are some places in the Earth where you have cracks that the heat can escape a lot easier than just regular ground. For example, volcanoes, fault lines, right? Geysers, just naturally occurring cracks. And that's where we can harness this geothermal energy. Right? Now, when we find a suitable location that has a crack or has geothermal energy close to the surface seeping out, we need to classify them as three major, or we need to look at them and classify them in what quality of geothermal energy there is, right? Is it good, medium, low? And there's different ways we can harness that type of energy. Okay, so what are three attributes that make a high quality geothermal source? First one is heat, right? The more the heat, more is better, right? The higher the heat, higher temperature, the more we could extract the energy to make electric energy or heat the homes and houses and other things. Another thing we need is water. Remember, we need to take the heat from the ground and bring it up to the surface to put it in the generator. Water will almost always be the best way to transfer heat. You put water in a very hot geothermal site, it turns into steam, pump the steam out, go to the turbine, and it will spin a generator. Okay, so we need to have good amount of heat. We need to have water, more the better. A third one is permeability. Basically, permeability means how many little holes and cracks there are in the rock to let the water flow. If it's solid rock with no way for the water to flow, we can't extract the energy. So it needs to be more porous. So rocks are kind of broken up, you got little cracks in them, or it's loose rocks everywhere. You just want the water to flow through. The better the water can flow with less restrictions, the easier it is for us to harness energy out. Okay, so heat, water, permeability are the three major things needed to start have a high quality geothermal source to start producing electric energy. Now, when we start talking about heat and water, we have to start thinking of thermodynamics and mechanical engineering. There's a key concept called enthalpy, which is the amount of energy capable of doing work. So each geothermal site has a set amount of energy, and how much of energy can we extract to do useful energy? It's called enthalpy, right? This amount of energy we can extract from work is a function of temperature, pressure inside the geothermal site, and volume, how big it is, right? Big volume, low pressure, we can still do something. High pressure, small volume, the high pressure helps, we could do something. So it's a combination of these three. Obviously, you have all three, you have the best one. If you have none of them, you have nothing. So there's some combination of them. Okay. So the big thing to take away here is we need heat, water, and permeability to get things going. Now, the question is how much heat are we talking about? And is there a pattern to the amount of heat? So there's something called a geothermal gradient we have to look at, which gradient typically means a sliding scale, right? Something that increases. So geothermal gradient is the concept that the temperature will increase as we go lower into the earth. So increase in temperature and increase in depth within the earth. So basically, if you look at this graph, at the surface, we don't have much heat because we have the outer, it's all radiating into the air, into outer space eventually. So where we live on the surface is not that hot. But let's say we go about 50 meters, 50 kilometers down, which is about 20 something, 30 miles ish, 30 change, right? That's pretty deep, 30 miles. All of a sudden, the temperature is about 600 degrees Fahrenheit. Or if we're underneath the continental crust is where we live in, or if you go 50 kilometers below the ocean's crust, which is at the bottom of the ocean, and then 50 kilometers more, I mean, you're much higher to 1,000 degrees Celsius, right? Because you're getting closer to Earth's core. We're still a long way to Earth's core, but the closer we get, the hotter it's going to be, obviously, right? So it just shows you the deeper we go under to the Earth, the hotter the temperature is going to be, right? And again, what dictates a good geothermal source? We need a high amount of heat, but for us to use it efficiently, it also needs to be close to the surface because we don't want to waste a lot of money drilling 100 miles down into Earth. It's almost impossible, right? So it's just kind of a luck of the draw with nature that we have a pocket of high heat that happens to be closer to the top layer where we live on. Okay. It's kind of a little image to show you if you remember from, I don't know, middle school, you learned somewhere. You have the continental crust is what we live on. The oceanic crust is where the ocean settles on. You go a little bit deeper, you have the lithosphere, and then below that you have the asthenosphere. And this is kind of where we start getting really high temperature. Because down here, this is where you have molten magma, everything's starting to heat up because the Earth's core is below that and is heating the whole Earth and is melting a bunch of metal and rocks and stuff down here. Okay. So just the big takeaway here is we got to drill deeper into the Earth to get a higher temperature. Okay. So I'm going to ask, where does geothermal energy even come from? Again, at the end of the day, the Earth's core is a giant ball of metal and nickel and some other elements and hydrogen and is constantly going through a fusion reaction to create heat. That's why our Earth has some warmth to it, right? Otherwise, it's going to be frozen in outer space. So Earth's core is constantly heating up, and then the heat radiates out into the lower mantle layers and the surrounding rocks, which then we live on top of, okay? Eventually, this heat can make its way up to the surface where we can harness it by cracks in the ground near fault lines. So if you ever have mountains or earthquakes, right? Say like San Andreas fault line, you've heard that here in California. That's where you'll typically find cracks in the earth where the heat escapes. Or we could be man-made where we drill holes into the earth to force it out. But it's very expensive, but we can do that. Okay. Some natural examples of a geothermal energy source rising to the surface is geysers and hot springs. You have some here in the national parks. This is just literally a vent for all the heat to spray out of, and you have all this steam and hot water. Okay. And remember, anytime you have steam and hot water, steam and heat nearby, we could put a generator on top and we can make electricity. Okay. So, what are classifications for geothermal sources so we can start installing generators on top of them? We typically have three sets. We have a high temperature source, which is classified any heat source above 150 degrees Celsius. We got moderate temperature sources. This is between 9 degrees Celsius and 150 degrees Celsius right here. And we have low temperature sources that are less than 9 degrees Celsius. Now, remember, 100 degrees Celsius is where we boil water. So 150 definitely means whatever water we put in there will turn into steam. Moderate temperature is kind of, you're almost at the cusp, depends on what type you have. Low temperature definitely means that you cannot create steam because it's not 100 degrees Celsius. It won't, the water won't boil. And that's a very big key part because we cannot use a steam generation plant to make electricity with a low temperature source. Okay. Which classifications are typically used for high electric generation? The high temperature source is always the best. We absolutely can't use low temperature sources. Moderate temperature sources is kind of a luck iffy, right? We probably tend not to do because it could go lower temperature and then we kind of lose all our money on investing in a plant. So if I'm going to make a giant electric generator, a geothermal plant, I want to make sure it's at a high temperature source so we have that constant heat and a constant electric energy production. Okay. So three classifications. Now, question is what material are we going to look at that we consider geothermal source? The first one, probably the most ancient one that we've seen, is molten magma. We know that molten magma is found deep beneath the Earth's surface. This is literally rocks and metal that got so hot that it melts down into liquid form. Okay. Sometimes you'll see the surface in terms of volcanoes. Remember, volcanoes are vents So you have too much pressure, too much geothermal energy, it pops out to the earth and it spews magma all over the place. And it's like a pressure relief valve for geothermal heat source. Okay. What are classifications for molten magma in terms of the three classifications? Definitely high temperature source. I mean, molten magma is like 1,000 degrees Celsius. That's really, really high because that's from deep in the earth. Okay. People theorize that if we could use molten magma for electric generation because it's 100 degrees Celsius, that's really, really hot. We can make an insane amount of electric energy, but there's some difficulties, right? Why is it difficult to produce energy out of this? Well, biggest one is what material do we have can withstand 100 degrees Celsius temperature? If molten magma is melted steel and rock, what are we going to make that can withstand 1,000 degrees Celsius to make electric generation? It's pretty much nothing. If we have a boiler and pipes, they're going to just melt into molten magma and just add on to the pile. So that's the biggest problem is there's no we don't have any material science solution to even harness molten magma at this point. Some people theorize you could use like electromagnetic fields to kind of harness it and all that. But I mean, that's so incredibly expensive. It's not going to be worth the hundreds of millions of dollars to create a plant to make, not even that much in its lifetime. Okay. So molten magma sounds like a good idea, but until we get some advances in material science, we're not going to be able to use it. Okay. But I mean, it's good to know it's there. Right. Next one is called hot dry rock. So this is deeper in the earth. You'll have literally rock that's super hot because of the core, right? And then if we can find them near a fault line and closer to the surface, we can then use it. So where do we find hot dry rock? Emphasis we, as in we discover it. It's near fault lines and anything that happens to be closer to the surface. It's kind of a luck of the draw. Okay. What type of classification do you have? Hot dry rock is a high temperature source for sure. This stuff is well above 150 degrees Celsius. I'll probably say it's more closer to like 200, 300 degrees Celsius, right? It's not that hot because the rock is still solid. Okay, it hasn't melted in the magma yet, so it's definitely not the 1,000 degree Celsius level. Okay, what makes using this energy difficult? Well, the biggest thing is we have to drill to it, right? This hot rock system is typically maybe 10 miles in the ground, and it's not going to show up on the surface for us unless maybe extremely rare times it will if there's like a fault line nearby or we got really, really lucky. But realistically, it's not going to be anywhere close. So what we're going to have to do is we're going to have to physically drill down there and make these pipes. So you can see in this image, we're drilling down into the actual rock system, hot rock system right here. And then we could pump water and get steam out. So this is a kind of a man-made well. And that's what we'll have to do to enter into this rock system. Okay. So that's always going to be the cost we have to pay to utilize geothermal sites. Okay. So it's kind of what we're talking about. How do we adapt using it? Well, how do we harness energy from hot, dry rock? One key thing, dry rock means there's no water. Okay. So this is no water, no steam. It's literally just heat. We cannot harness heat from the ground up into the surface with just air. It's very inefficient. So we would have to inject water into the system. So we drill a bunch of pipes into hot rock and dry rock, and then we inject water. We're going to force with pumps into the ground. It's going to hit the hot dry rock, and then it's going to immediately flash into steam because it's so hot. Once it's steam and pressurized, we pump it out a second pipe into the generator, and now we can make electric energy. So that's how we harnessed it. We had to pump water into it. How can we? So let's say the hot dry rock is too solid. Let's say the water won't flow into it. It's just a giant solid rock. Well, we can fix that too. We can increase the permeability of rocks by breaking them. Now, how do you break them? You can force high pressure liquid during the drilling process down into the well and kind of shock the system and break the rocks. Another term for this is called fracking, right? Where you go and you put fracking fluid in very high pressure. You put a sudden pressure shock into it, and it'll go into all the cracks and split open the rocks. Once you split it all open, now you got these micro cracks everywhere. That's where the water can flow. Okay, so this is a man-made issues where we're forcing the rocks open, we're drilling deep into it so we can access the heat. Okay, what's a nearby geothermal plant over a hot dry rock system? We actually have one very close. It's called the Geysers in Northern California. It's kind of north of San Francisco. It's probably one of the most famous geothermal sites in the world. Here it's 750 megawatts, so that's pretty big, right? That's probably, just to give you an example, a decent sized coal plant might be 1 gigawatt or 1,000 megawatts, maybe 2,000 megawatts. So 750 megawatts is on the size of a traditional power plant, which is pretty big. Okay. All right. So that's hot dry rock. Another naturally occurring geothermal source we can find is a geopressurized reservoir. So the idea is we have this cap rock that naturally will grow over thousands, hundreds of thousands of years. If you remember from talking about oil and fossil fuel, a cap rock is solid and it traps everything underneath it. That's how oil is formed, right? So a cap rock here is where we don't have oil because there's no dead plants. Instead, it's going to trap the heat. Okay. And then if we could drill through the cap rock, we could probably access this geothermal heat reservoir and use that for electric generation. Okay. So where do we find geopressurized reservoir? Underneath cap rock formations. A lot of cap rock formations formed in the Gulf coastline, meaning Texas, Louisiana, some Mississippi, and stuff like that, and Alabama. But typically, it's just how nature is formed for millions of years. It's just southern parts of southeastern parts of the United States has a lot of these cap rocks. That's why we have oil everywhere, and that's why we have the possibility of a geothermal reservoir as well. Okay. How do we classify geopressurized reservoirs? This is a high pressure source because there's nowhere for the fluid or any of the heat to go because cap rock blocks it. So it's going to build up pressure, it's going to build up heat. So this is definitely above 150 degrees Celsius. Okay. And there's going to be a heat source below here that's going to continuously add more heat into this pocket. And it's just going to go on forever. Okay. How do we capture energy from this reservoir underneath this cap rock? Well, we have to first drill through the cap rock to access the reservoir. And then we're going to pump hot water into it and then use that water to extract the heat. Okay. Now, because of the way cap rock here, things get trapped a lot, we might actually have a little bit of methane mixed into as well. So you can have like a little bypass system to harvest methane for fossil fuel use as well. Okay. So geopressurized reservoirs, they're kind of littered here and there. And if you find one, you're willing to drill for it, you can pop a generator on top of it and it'll pretty much give you free energy. Right? It's good stuff. Next one we're talking about is hot water reservoirs. So here is you have a heat source down below, and then above it is water. And then we have a natural way to get the water, right? So it's kind of like what dry rock would have been if water happens to be present nearby. Okay, where do we typically find hot water reservoirs? We typically find it along fault lines because there has to be a natural crack for the water to seep into. So think about water rains in the mountains. It kind of flows down in a river into a valley, and this valley will happen to have cracks in the ground that the water will seep all the way down, hit this hot rock, and then flash over to steam, and it will kind of collect right here as hot boiling water. Okay. Now, the question is, what classifications are hot water reservoirs? They actually vary widely. Some are high heat sources, other are moderate heat sources. It really depends on how big the hot rock bed underneath it is, number one. And number two, how much water naturally flows into it. Okay, so it's kind of like look at the draw top stuff. So the question is, how can we use this? We can use something called organic Rankine cycle. Remember, Rankine cycle is using steam with a turbine to produce electricity, but this might not be hot enough for regular steam, so we can use an alternate liquid that has lower boiling point to try to use this system. That's why, and this alternate fuel or this alternate liquid is typically some organic liquid. That's why it's called an organic Rankine cycle. Okay, so think about your standard steam generation plant. We just modified it a little bit for the lower temperature of the hot water reservoir. Okay. So as you can see, there's different levels of geothermal sources, and if we're smart enough, we could use different generation types and systems to harness all levels of geothermal sites because every one of them is useful in some form or fashion. Okay. So we talked about the high temperature ones. Let's talk about more of the intermediate and low temperature sources. So here, these are the sources that aren't good enough for electric generation because the temperature is just too low. Temperature geothermal sources too low, we can't use for electric generation. That's it. Okay. There's other things we could use it for. We could still use it for district heating and heating water and other smaller things. So, for example, you might have this little greenhouse or this structure. We could drill pipes into the earth where the earth is not going to be super hot, but it's still going to be warmer than what it is out here in the winter. And we could pump water through these pipes and get some amount of free heating for our system, right? Because if you drill a couple hundred feet down into earth, it's going to be warmer than what it is on the surface in the winter. Not boiling hot water, but it could be like maybe 100 degrees Fahrenheit, maybe 115 degrees Fahrenheit, right? That's enough to pump some heat into your house to keep your house a little bit warmer in the cold winter. And that's what we're looking at here, okay? Lastly, we could have just straight up normal ground temperature sources. This means there's no specialized heat source where we live. It's just straight up dirt. We can still use it to some effect. If you dig 1 or 2 meters below the earth, the temperature of that soil and water is typically a constant 10 degrees Celsius or 50 degrees Fahrenheit, right? The sun hits the surface on the grass and the pavement, that gets hot, but about 1 or 2 meters down, that heat's gone and we have a near constant soil temperature. We can use that by taking our house and building a pipe about let's be safe, let's say 10 meters down in the earth. Put a bunch of loops of pipes everywhere to get a little more surface area, and then pump some water back up in the house. So we can reliably get a 50-degree Fahrenheit temperature source from the ground, because the ground's never going to change. It's constant all day long, right? In the winter, we could take that 50 degrees and help heat our home a little bit, because let's say in the winter, if it's snowing, it could be 20 degrees Fahrenheit outside. That's pretty darn cold. So pumping 50-degree water into our house will elevate it higher than 20 degrees where we get outside, right? So it's kind of like an additional system to your heater to help bring the temperature up a little bit, okay? In the summer, on the opposite side, if we have 100 degrees Fahrenheit outside the house, like we do here in Turlock, it might be nice to pump 50-degree Fahrenheit water into the house to cool off the house if you have a bunch of pipes everywhere, okay? So you're basically just using the temperature in the ground as a reservoir, we call it, okay? Since the temperature is always stable underground, we can use this ground temperature source as a heat reservoir in the winter. So we could pull heat from it. And in the summer, it's a cooling reservoir where we could pull cooling in the summer, right? Give me one sec. Okay. I kind of miswrote that. This should be in the summer. So let me change it real quick. Blue. Summer. Good enough. Okay. Okay, so that's our normal ground temperature source. So there's different versions we see. And one thing about this normal ground temperature source, you could use this anywhere. As long as you could dig about 10 meters, 5 meters into the ground, you can use this system. Okay. We don't really typically use it here in California, but in the northern part of the United States and Europe, this is more extensive. Almost some places, every house has this system built in. It's part of just a normalized neighborhood building template they use. Okay. All right. So we talked about all the different type of sources naturally occurring that we have. Let's take a little break real quick, 15-minute break. Let's have exercise. I want to talk about the Geysers geothermal plant. We talked about it once. I want you to go do a little Google research, figure out what the Geysers geothermal plants are. Find a unit capacity, what types of geothermal site it is, the ratings, how much power it produces, any other relevant information like the who owns them, blah blah blah. Right? I would strongly not use Wikipedia because that's unverified. Go to their main website; they have a lot of nameplate data for you, so you can figure out and just kind of list out what you find. And we'll come back in 15 minutes and compare what you got. Okay. So that being said, we'll stop the recording and see you in a little bit. So good luck. All right, hello everybody. Welcome back to EEE 135, Chapter 10, Geothermal Energy Sources. Here we're going to review the Geysers geothermal plant and what it's about. So basically, it's owned by Calpine Corporation. I believe it's like 85 or 9% owned by them. Very small stakes by NCPA and a few others, just I guess have a say on the board. But the majority is Calpine Corporation, right? Location is about north of San Francisco, about like, I don't know, 50 something miles. Basically on that fault line, right? Capacity is 725 megawatts that they run pretty much year round, I believe, barring some, taking a few wells off for maintenance and whatnot. In terms of the geothermal specs, there's 322 dry steam wells. They're roughly about 367 degrees Fahrenheit temperatures. This is average. And the site's about 28,500 acres. So that's a lot. Think about, just to give you a perspective, a California home is probably on a quarter acre lot. So this is probably 100,000 homes equivalent in terms of space usage, right? So overall, I mean, this is a good system. It runs, it helps California, generates power. This is not stopping anytime soon, and it's pretty famous because this is really big for a geothermal site. So I think Northern California got really lucky that we naturally have a gigantic hot dry rock bed near there that's close enough to the surface where we could easily tap it, right? All right. Excuse me. So we talked about the sources underground. Let's start talking about what's on top, the actual generation plant and the systems used to convert geothermal heat to actual electricity. There's 5 major plant types we can use based on the type of geothermal sites, the lack of water, and the temperature. Number 1 is a dry steam plant. This is basically probably the best, right? But it's also the hottest. Next one is a flash steam plant. This is basically where you inject water is getting flashed up to steam, and then we just run a regular turbine. Double flash steam plants basically you have 2 cycles of making steam instead of one. You have a high pressure, high temperature steam plant and a low pressure steam plant, and they'll kind of work in a 2-stage process to make electric energy. Binary cycle plants is basically there's 2 cycles that we go through, like injecting water, taking it out, and whatnot. Oh, sorry. Binary cycle plant is you have 2 water loops where you have one water loop that hits the groundwater or the geothermal heat, and then it transfers energy through a heat exchanger to a second liquid loop for electric generation. And there's reasons why you want to split those water loops apart because you don't want contamination to spread to the generator. Lastly, it's enhanced geothermal system. This is basically a purely man-made system where we do a lot of drilling, a lot of work to tap into a geothermal site, and we inject the water, and we pretty much make a geothermal site, and then we harness it for electric generation. Okay. All these systems have a few things in common that make them an ideal electric energy source. Mainly is the heat's free. The whole point of geothermal is that the heat is coming from the center of the earth, which we don't have to pay for, and it's hot enough to run a conventional generator, so it's run 24 hours a day. We don't have to worry about the whole weather pattern, intermittent issues with the wind turbine or the PV panels with the sunlight. This is as close as we could possibly get to a fossil plant that's ran 24 hours a day. This is why everybody loves geothermal, because we're not really making new problems. We're just adding more solutions and helping the grid out without asking for, like, I need extra energy storage for the nighttime and all this other shenanigans that we have to deal with other renewable energy sources. So, I mean, people love this stuff. All right, let's talk about dry steam plant. Dry steam is basically steam that's so incredibly hot that there's no more liquid water suspended in the air. So you've ever heard of steam, right? You'll probably, if you ever got like medium level steam blown on you, you might see like, oh, there's some, your hands get a little condensation water on it because there's still liquid in the air. But if you get so incredibly hot, all the air in the, sorry, all the water in the air will also turn into steam, and then you'll never get wet. It's just going to be really, really hot steam that's going to burn your skin off, right? So the temperature of dry steam is 235 degrees Celsius, or in freedom units, 455 degrees Fahrenheit. Okay, just to give you a better idea, right? You touch this, you're getting a new arm type of level. Okay. The process to produce electric energy from this type of dry steam is you need to have production wells, basically pipes you drill into the ground that pulls the steam from a geothermal source. So there's steam underneath, we pull it into our generation system. The dry steam will then, number two, the dry steam will enter a steam turbine that will turn a generator to produce electricity. The used steam will have to enter a condenser and lower the temperature of the steam so it will naturally form back into water. So if steam ever gets below 100 degrees Celsius or 212 degrees Fahrenheit, it'll start condensation, and then it will turn back into liquid form. And we want that. We will then inject the liquid back into the geothermal source through another pipe and let it heat up back into dry steam. And we're just going to repeat the process over and over and over again. Okay. So here's a diagram to show you. Is you got your hot geothermal site. This is where the water is. Notice the water will flow across. It will turn into dry steam because the temperature is so high. And the steam will pop out of the production well. It pops out pretty fast. So you have to have a rock catcher, because basically this is, if you have any debris or rocks that get knocked off over a course of years, you don't want to go to a turbine because a rock in here will smash all the blades. So we can have like a little net. So the high pressure steam shoots out and shoots out the rocks, kind of like bullets almost. The rock catcher will catch and dispose of it. And then the rest of the steam will go to the turbine. We've seen this plenty of times. Hot steam enters turbine. There's fins everywhere. It spins. Spins alternator, just another way to say generator. And then the generator will produce three-phase power, which then goes to step-up transformer to transmission line. Now, once the high pressure dry steam enters the steam turbine, a lot of the heat will be lost because we're letting it expand. And as the steam expands, it spins the turbine like a fan. So when it exits, it's like low temperature steam. We're not done yet. We talked about this before. You have to put it back in the liquid form. So you have to have some secondary piping system, some radiator and cooling towers here to let it naturally drip back into liquid form. Once it's back in the water, liquid water, you then inject it back into the well, and you just keep going over and over, and this is an endless cycle. Okay, so long as you have water to pump in, it will naturally keep pulling this over and over and over again. Okay. That being said, a lot of times you have a cooling tower, you probably have a lake nearby or a river nearby to add extra water in, because the cooling tower, you need to put water in here to then take the heat out from the condenser. So one thing I want to point out here, the geothermal site, remember, this is where water turns into dry steam again, and this is how the cycle continues. Good to note that the temperature difference between the water coming in and the heat, the high temperature dry steam going out, the bigger the temperature differential, the more power we're going to make. This is why we can't just inject the low pressure steam back into the geothermal site normally. It's not going to absorb some of the heat. It's going to be inefficient. So we always want to get this liquid as cold as possible to pop it back in so we could obey the laws of thermodynamics and extract as much heat as possible. Okay. So that's your dry steam plant. So I guess I would mention, apart from the heat source, everything else, this middle part, this is the same way a fossil plant works. A coal plant, a nuclear plant, they all work on based on a steam turbine. The only difference is just where the heat source is coming from. And there's, in this case, it's a geothermal source. Okay. Another version is a flash steam plant. This is flash steam is basically a mixture of pressurized hot water and steam when the pressure is released. So think about a can that you have water, you heat it so high, it wants to expand into steam. So remember, when water goes to steam, it physically expands, it turns into gas form. You need the volume to let it happen. So if you don't have the volume, it's going to stay as water. And it's going to get higher and higher pressure. I mean, higher temperature. It'll go past the boiling point, but because you don't have the volume to let it expand, it's going to stay liquid form. Okay? And that's what flash steam is. Because whenever you release the pressure, the really, really hot water will instantly poof into steam and expand at a rapid pace. Okay? The temperature of flash steam is typically about 182 degrees Celsius or 360 degrees Fahrenheit. So note it's lower temperature than dry steam. Okay? The process to produce electric energy for a flash steam plant is the same as a dry steam plant previously with a Rankine cycle, except we add an extra step because we are getting water, very hot, very pressurized water from the geothermal source. We need to have a step to let it expand into steam before we throw it into the steam turbine. So we need an extra step as a separator. Okay. So here's kind of an image to show you what's the extra step we added. Well, the production well will pull this flash steam. So it's basically really, really, really high pressure water and steam. It's going to come out. It's going to go to a separator. Okay. Now notice once it goes to separator, it's a big tank. It lets the volume expand. As it expands, some of this liquid will turn into steam. Not all of it. So some of it will go down to hot water. So it's kind of like a separator in terms of 80% of your heat of your liquid goes into steam, but then a low 20% of liquid will stay liquid, and you have to just put that back into the system, right? You can't really use that. Okay. So production well pulls a flash steam to a separator, and the separator expands the volume for the steam to flash over, and then it splits the steam from the water. Then the steam goes into the steam turbine, and we produce our electricity like normal. Notice how hot water is called wastewater because we can't use it for electric generation, and we just inject it back into the well. You just cycle it back and forth. Think of it like a tax you have to pay. Nothing's 100% efficient. That's just part of the system. You just let it go and just redo it over and over again. Okay. Again, remember we need a condenser because we want to take the steam out of the steam turbine, bring it to as low as temperature as possible to add it back into the well as well, and back into the steam geothermal source at the bottom. Okay. So a very similar process. You just have this separator as extra step. Okay. A double flash steam plant is where the source heat is very hot and under high pressure. So this water is much hotter than the previous one, and it's under very high pressure. Okay? So it's different from a dry steam plant. It's different from a single flash steam plant. Okay? The temperature of a double flash steam plant is 250 degrees Celsius, so it's 482 degrees Fahrenheit. So it's hotter than a single flash steam plant, and we could utilize that because it's hotter. the process to produce electric energy is the same as a single flash steam plant, except after the first stage of separation, the water is still so hot that we could have a second expansion system and a second layer to separate the steam even more. So it's like double dipping into our source. And then we run that into the secondary steam, we run that into a separate low pressure steam turbine, which is built differently to run a second generator or in tandem with the main generator. Basically, you have two steam turbines on the same shaft of the generator to produce more power. So think about that. Think about this way. The steam is so hot, we could use it twice. That's what the double stands for. Okay. So here, what extra steps do we add from a single flash steam plant design? We got the really hot flash steam coming out. You have your high pressure separator right here. So you get high pressure steam, you get water coming in here. And remember, just because it expands doesn't mean this is ambient pressure in the air. It's still high pressure within the separator, but it's lower pressure as compared to underground. So we kind of let 50% of the volume increase to let some of the high pressure steam go. So we still have hot water under pressure. We're going to go to a second separator with more volume to let more steam flash over, and then we'll dump the wastewater. So we have two separators, a high pressure system and a low pressure system. Notice that both the high pressure steam goes to a steam turbine. This is called a high pressure steam turbine. And a low pressure steam goes to a low pressure steam turbine. Again, is built differently. And they both are on the same shaft to the generator and can produce more energy than just one. Obviously, you have two turbines in one shaft. You might not be producing double the power, but you're at least producing an extra 50%. So you're getting more out of the same source. Okay. So yeah, what extra steps do we added for a flash steam plant? A second low pressure separator to extract low pressure steam, and a second turbine to increase power to the generator. Notice that both of these have to come out to the condenser, because the condenser again has to make the steam turn into liquid again to go back into the well and then go through the steam geothermal source on the bottom to raise the temperature back to the high pressure flash steam to then enter the system again. And this is just a continuous cycle. You're just putting water in, pumping steam up, and you just do this forever until you run out of heat, which if you do this slow enough, you're never gonna run out of heat. And it'll be a forever thing. Okay. That's why people like geothermal sites. So more complicated system, but it's more efficient. It's like a second stage of energy extraction. Okay. Another system we can use is called binary cycle plant. This is where we have two separate steam loops, right? Very small typo here to fix. It's not separator, it's separate. So two separate steam loops. Liquid and loops are isolated, meaning they'll never mix. Okay. What type of fluid is typically used in a binary cycle plant? The ground loop, which is the liquid loop that goes in the actual geothermal source underneath the ground, has some type of corrosive brine water. It's probably natural to the geothermal site itself. We can't help it. Basically, the geothermal source has some corrosive material and elements, and it's just going to mix into our system. We can't do anything about it. We got to live with it. Okay. But if we isolate that loop only to the heat exchanger and the geothermal source, we're lessening the damage to the system. Okay. Then we have a secondary loop that has a low temperature oil to carry the heat to the generator. So it's like having a buffer so we're not mixing corrosive liquids to the actual steam turbine and generator. Okay. The process for electric energy production is the ground loop heats up its heat exchanger. So the liquid in the geothermal source pops into a heat exchanger up on the surface. The heat exchanger gets hot. And then the oil is also ran into the heat exchanger. So they're both running into the same piece of metal. and it'll naturally transfer the heat over. Okay, this oil, because it's low temperature, will vaporize pretty quick, kind of like steam, and then the vapors are then ran through a turbine to produce electricity. Now, this oil will probably have a lower boiling point than traditional water, and it'll make up for the inefficiency of a heat exchanger, because the heat exchanger will never convert all heat over. It might only be like 60% efficient. So we have a low temperature oil to help mitigate the difference. Okay. This is again called an organic Rankine cycle. Rankine cycle is a standard steam plant, where organic means this oil is probably some organic low temperature oil. Okay. Kind of show you an image of what we're talking about. Here you got your production well. Well, what is the changes from previous geothermal plants design? Mainly, we have two separate liquid loops that transfer energy. So here we have a geothermal heat source on the bottom. We're going to inject water in. There's going to be some corrosive material and brine. So it's going to come out. Rock catcher is there, and it's going to go into the heat exchanger, and it'll dissipate the heat into the heat exchanger naturally. Okay, kind of like a radiator. Within the heat exchanger on a separate loop, but nearby, you're going to have your secondary loop where you're going to have that low pressure oil. The low temperature oil, that the liquid will go into the heat exchanger. Is hot enough, it will vaporize into, quote, steam. And then the vapors will go into the turbine, spin the turbine to make electric energy. And then the same thing comes out. We need to lower the temperature of the oil back in the liquid form. And we'll just keep doing the system over and over again. So you basically have two sets, two pumps, two water loops, and they're interacting with each other with this heat exchanger. Okay, this is a good system for low heat geothermal sources that can't produce steam naturally. So let's say the energy source here is not hot enough to produce pure steam or this corrosion. This is a secondary system where we can still utilize it without throwing it away. Okay, it's a good system. It's a little more complicated because you got two loops and more maintenance, but it's better than nothing, right? So it's a good design, in my opinion. Okay. Lastly is a enhanced geothermal system. Basic definition is a geothermal site is literally artificially made. We go into a site and we do some surveying. We know there's some warm temperature underneath, but other than that, there's no water. It's not porous. It's just heat. Well, we do enough power, we could force nature and bend it to our will. We basically go in, we start drilling down, we start fracking the whole area, make those cracks, and we're pouring a bunch of water in, and now we have a geothermal source. Okay. So how do we add permeability to rocks to increase the heat capacity? You break rock bed up into millions of cracks to let the water flow. Okay. And once the water flows, we can put a plant on top, and we're in business. Okay. Process to produce electric energy is we have to inject water into the new geothermal source. It's not naturally there. We need to capture a new steam in a production well and run the steam through a Rankine cycle to produce electricity and you want to keep injecting water back in. Okay, you just want to do this over and over and over again. Okay. It's kind of image of what a geothermal site's going to look like. Notice you have all these pipes to the ground. So this is where we're pumping water in. It's going through a couple tanks and it's kind of going back out. This is a more large scale what a geothermal plant is going to look like. You got a bunch of stacks everywhere. You probably have where we're going to dissipate the heat and all this other good stuff. Okay, so there's a lot of work involved in this type of stuff, especially if it's man-made. Okay. All right, so we covered a lot today. Summarize everything. Geothermal energy. What are different types of geothermal sources we see in the earth that could be utilized? Molten magma is the one we observed for the longest because it's volcanoes that pop out. It's very hot. Maybe one day we'll be able to utilize that. The other one is hot, dry rock on the ground. We could drill to. Perfect energy source right there. We get geopressurized reservoirs kind of in the Gulf area where you have the cap rock and then some heat builds up underneath it. We could drill through the cap rock and then extract that heat for use. Hot water reservoirs. This is a naturally occurring valleys where rain seeps into the earth, goes into a geothermal site near the surface and heats up, and then bam, we got our water source and we got a heat. We can make use of this. Other things are intermediate low temperature sources. This is not for producing electric energy. It's more for heating your houses and melting snow and other heat related stuff for basically us to use. Okay. Different types of geothermal electric power plants we have design wise. We got dry steam plant, flash steam plant, double flash steam plant, binary cycle plant, enhanced geothermal systems, and it's just typically one of those two. You will choose which type of plant based on the classifications of your geothermal site and if there's the availability of water and permeability and all this other stuff. Okay. So you basically choose the best one you can with what you got because it's pretty hard to change geothermal sites. They're very expensive. It's better just to find a suitable location, build a plant that matches what you have, and it saves money. Okay. Biggest geothermal plant in California is the Geysers in Northern California. It's roughly 750 megawatts production. It's a dry steam plant and it's very famous in geothermal world. Okay. So with that being said, that's all I have for today. Don't forget to come back on Wednesday to watch the second set of videos where we're going to start talking about the low temperature applications and how do we use geothermal energy for other things besides electric generation. Okay. So thanks for showing up. Hope you guys have a good rest of the week and see you in a few days. Later.